Hello students, I am Laxman Singh Rawat, PGT Chemistry at CIS Dasua. Students, I hope you are enjoying this method of teaching learning that CIS Dasua has come up in this hours of crisis. CIS Dasua's e-learning is helping students to study at their home so that they do not lag behind due to this lockdown. We will continue with our chapter, The Structure of Atom. Today we shall be discussing the Planck's quantum theory or the quantum theory of radiation. Let us take a quick recap of the previous topic which we had discussed. Also remember that in vacuum, all type of electromagnetic radiations, regardless of wavelength or frequency, they travel at the same speed, that is 3.0 into 10 power 8 meter per second, or 2.997925 into 10 power 8 meters per second to be more precise. And this is the speed of light and is given the symbol c. Let us discuss the characteristic of wave motion. First we'll discuss wavelength. Now what is this wavelength? The distance between the two nearest trough or crest is called the wavelength, or the distance traveled by a wave in one complete cycle is wavelength. So the distance between successive crest or successive trough is the wavelength. In the diagram, in the figure which we have given here, you must have seen that the waves is in two directions, one in the positive direction and another in the negative direction. So the mean point is called the node, okay? And the wave in the upper direction than this one is positive direction, and lower than this one is the negative direction. So starting from mean and reaching the mean again after moving through the negative direction, complete positive direction, then negative direction, and then node again, that makes one complete cycle. So the distance traveled in this one complete cycle is the wavelength. So lambda, or the wavelength, is distance between two consecutive crests, or this can be considered as the distance between two consecutive troughs, or it is equal to 2 into the distance of two consecutive nodes. The wave has two phases with two different algebraic sign, the positive and negative. Upper is normally taken as the positive, lower is normally taken as the negative, separated by a zero amplitude regions called the nodes. The mean portion, the mean line at the center is called the node line. Frequency, denoted by nu, it is defined as the number of waves passing through a given point in 1 second. The SI unit of frequency is Hertz, denoted by Hz. Also, it is expressed in cycle per second. 1 cycle per second is equal to 1 Hertz. Now, we have got two wave trains here. The upper one, which has shorter wavelength, has higher frequency, whereas the lower wave train, which have got longer wavelength, has low frequency. If we see the distance of the two waves here, the distance is same. Let us suppose this distance is covered in 1 second. So the high frequency wave train, it has 12 waves passing through a point in 1 second, and the low frequency wave has 4 wave train passing through a point in 1 second. So more the number of waves complete cycle passing through a point in 1 second, higher will be the frequency. Lower number of complete wave trains passing through a point in 1 second will have lower frequency. Now wavelength is the distance traveled and frequency is cycle per second. So the product of this one is equal to the distance traveled in 1 second. That is, nu into lambda is equal to the velocity, or the frequency nu equal to c upon lambda. This is how we can find out the frequency. The velocity, it is defined as the distance covered by wave in 1 second, denoted by c. All electromagnetic waves travel with the same velocity, as we have already discussed, and the velocity is 3.0 into 10 power 8 meter per second. That is the speed of light. So nu into lambda equals to c, and that should be equal to 3.0 into 10 power 8 meter per second. Now since all the electromagnetic radiations, they are traveling with the same speed, thus a wave of higher frequency will have shorter wavelength, while a wave of lower frequency will have a longer wavelength, because nu into lambda is constant. So if nu is longer, lambda has to be smaller, or if lambda has to be longer, then nu has to be smaller. Wave number nu bar, it is defined as the number of wavelengths per unit length. So in 1 unit length, whatever the number of waves are, that is the wave number. Its unit are reciprocal of wavelength unit, that is meter inverse. However, commonly we use centimeter inverse also, which is not the SI unit. So nu bar is equal to 1 upon lambda. Next characteristic is the amplitude. It is the height of the crest or depth of the trough of a wave and is denoted by A. So it is the maximum displacement from the mean position in any direction, either positive or negative direction. It determines the intensity of radiation. The intensity is proportional to the amplitude square. The node is the point of zero amplitude. So the mean position is basically the node position where the amplitude is 0. Next is your time period. The time taken by the wave to complete one cycle or one vibration is called the time period. So T equals to 1 upon nu, that is 1 upon frequency, that will give us the time period. Now let us start with today's topic. The particle nature of electromagnetic radiations, or Planck's quantum theory. The wave theory successfully explains many properties of electromagnetic radiations like diffraction, interference, reflection, refraction, etc. What is this diffraction, reflection, refraction? It is given in this figure here. Reflection is the bouncing back of the light when it falls on any object. Refraction is the bending of light when it passes through any of the medium. Absorption is the retention of energy by any object. Then diffraction is the bending of light or the bending of wave around an obstacle. Now, what is this interference? Interference is the combination of two waves of the same or different frequencies to give a wave whose distribution at each point in space is the algebraic or the vector sum of disturbances at that point resulting from each interfering waves. This can be of two types, the constructive interference and destructive interference. In the case of constructive interference, the two waves combine to give a resultant wave whose amplitude becomes greater than either of them. And in the case of destructive interference, the two waves combine to give a resultant wave whose amplitude is less than the individual waves. Detail of diffraction and the interference you will be studying in physics. So what we are discussing is the wave theory was successful in explaining many of these facts like reflection, refraction, interference, diffraction. However, there were many facts which could not be explained by the electromagnetic theory, also known as the classical physics. For example, it could not explain the nature of emission of radiation from hot bodies, that is also called the black body radiation. It failed to explain the ejection of electron from metal surface when radiation strikes it, and that is your photoelectric effect. It could not explain the line spectra of atom with special reference to the hydrogen. All these phenomena points to the fact that a system can take up energy only in discrete amount. All the possible energies cannot be taken up or radiated. A detail of this one we'll be studying here. In fact, we will be studying about the black body radiation, photoelectric effect and the atomic spectra in detail. Now let us discuss Planck's quantum theory in detail. In order to explain the black body radiation and photoelectric effect, Max Planck in 1901 presented a new theory which is known as the quantum theory of radiation. It was further extended by Einstein in 1905. Let us discuss the main points of the theory. The first point is, a hot body emits radiate energy not continuously but discontinuously in the form of small packet of energy called quantum, and the plural of this is quanta. That means whenever a body is heated, it starts to emit energy, but this energy which is emitted is not continuous but discontinuously in the form of packets, and these packets were called the quanta. You can assume this one as if we are talking about the energy as we move on the ramp and the stair. In the case of ramp, you can take any number of steps, or the length of your step can be long or short. You will climb continuously in the ramp. However, in the case of stair, you will have to take certain number of steps only. In between those steps, you cannot take any steps. The energy associated with each quantum is directly proportional to the frequency of radiation. That is, E is proportional to nu, or E is equal to h nu, where h is a constant known as the Planck's constant. Its numerical value is 6.624 into 10 inverse 27 erg-second, or it is equal to 6.626 into 10 inverse 34 joule second. Here, the energy is correlated with frequency of radiation, which was not the case in the case of the electromagnetic radiation. The energy emitted or absorbed by a body can be either one quantum or integral multiple of it. That is, it can take up value 1 h nu, 2 h nu, 3 h nu, and so on, quanta of energy. Thus, the energy emitted or absorbed is equal to integral multiple of h nu, that is n h nu. Since nu equal to c upon lambda, we can write this equation as nhc upon lambda, where n can take up the values 1, 2, 3, 4, etc. Thus, we can say that the energy is quantized. That is, the energy is emitted or absorbed in fixed quantum of value. That is, they cannot be absorbed or emitted continuously. It was in 1905 Einstein pointed out that light can be supposed to consist of a stream of particles called photons. The energy of each photon of light depends upon the frequency of light, that is, the energy is given by E equals to h nu. The energy is also related according to Einstein as E equal to mc square, where m is the mass of photon. So when we say E equals to h nu, we are talking about the wave nature of light. And when we say E equal to mc square, we are talking about the particle nature of light. Thus, it was pointed out that light has waves as well as particle characteristic. That is, the light has dual nature. One Einstein is equal to energy of 1 mole quanta, that is energy of Avogadro number of quanta, and that is equal to Na, Avogadro number of h nu. Nu can be written as c upon lambda, thus the equation can be written as NaHc upon lambda. This is the energy, 1 Einstein is the energy of 1 mole of quanta. The quantum of energy can be written in different forms. Some of these are given here. E equal to h nu, where we are relating energy with the frequency of radiation. Since the frequency is equal to 1 upon t, that's why the energy in term of time period can be written as E equals to h into 1 upon t. Since nu equal to c upon lambda, thus we can write E equal to sc upon lambda, or in term of the wave number, E is equal to hc nu bar. Now let us try to solve a numerical based on what we have understood. Calculate the energy of 1 mole quanta of radiation whose frequency is 5 into 10 power 10 second inverse. We will require certain facts here. The Avogadro number Na is equal to 6.022 into 10 power 23. H is the Planck constant and it is equal to 6.626 into 10 inverse 34 joule second. Frequency is equal to 5 into 10 power 10 second inverse. Since energy of 1 mole quanta is equal to nh nu, where n is the Avogadro number, h is the Planck constant and nu is the frequency. Putting these values, we have energy of 1 mole of quanta is equal to 19.95 joule per mole. Let us solve another numerical here. Find the energy of a photon of light having a wavelength of 6000 Armstrong. Here h is equal to 6.624 into 10 inverse 27 erg-second. It is given. Let us solve this numerical. First, let us write all those quantities which are given here. The wavelength lambda is equal to 6000 Armstrong. Since h is in erg-second, so we will convert this into centimeter. So this is equal to 6000 into 10 inverse 8 centimeter. Speed of light c equals to 3.0 into 10 power 8 meter per second. In centimeter, this become equals to 3.0 into 10 power 10 centimeter per second. Since we know that E equals to h nu, or this is written as E equal to hc upon lambda, because wavelength is given. So putting the value of wavelength, speed of light, h in E equal to hc upon lambda, we have E equals to 6.624 into 10 inverse 27 into 3.0 into 10 power 10. This is h into c upon lambda. Wavelength is 6000 into 10 power 8. We have put this value. When we solve these quantities, we get E equals to 3.312 into 10 inverse 12 erg. The mathematical calculation you can carry out. Let us see another numerical here. What is the ratio between the energies of two radiations, one with a wavelength of 6000 Armstrong and another with 2000 Armstrong? Here, the value of lambda 1, we have taken it as first. Lambda 1 equals to 6000 Armstrong and lambda 2 equals to 2000 Armstrong. We have to find out the ratio between these two. So the energy 1, E1 equals to, for wavelength 1, we have E1 equal to hc upon lambda 1, and the energy of second wavelength is E2 equals to hc upon lambda 2. Therefore, the ratio of the energy of these two wavelengths, E1 upon E2 equals to hc upon lambda 1 divided by hc upon lambda 2. So hc cancels out. We are left with lambda 2 upon lambda 1. And when we put these value of lambda 2 and lambda 1, we get E1 upon E2 as 1 upon 3, or E2 is equal to 3 times of E1. Today we discussed the Planck's quantum theory or quantum theory of radiation, and we solved few numerical based on these concepts. In our next lecture, we'll be discussing further in this quantum theory. Till then, take care and thank you.